Yeah, thank you very much. So maybe recall from last time. So we introduced the Seyffering's intersection number. So if you have gamma, simple non-degenerate Reeb orbit, and you have U tilde, V tilde fast finite energy planes asymptotic to gamma, and then we define Seyffering's intersection number. These two as we perturb one of the curves asymptotically and then add one. So we have idea. So we have these two curves, U tilde, V tilde, and then we perturb U tilde. So tilde epsilon beta. And this has the following properties. So we have the following inequality. So we have, so if U tilde and V tilde have different image, then we have 0 is less than or equal the algebraic intersection number. This is by positivity of intersection. And this is bounded from above by Seyffering's intersection number. And in most cases, this is actually equality. In most cases. Equality. And then we can compute Seyffering's intersection number. So if U is UA, then Seyffering's self-intersection number, U tilde with U tilde, is given by the number of intersection points of U with the asymptotic orbit gamma, set T in C times S1, U set equals gamma T. So in particular, if U does not intersect the asymptotic orbit, Seyffering's self-intersection number is 0. And then, important property, if Seyffering's self-intersection number is 0, this implies that U from C to sigma is embedded. This is what we proved yesterday. Questions to what we did yesterday. Then let me mention 2 more things before we finish this discussion. So another application of Seyffering's intersection number is so assume Seyffering's intersection number U tilde is 0, or equivalently U does not intersect the asymptotic Reeb orbit, and V tilde is homotopic to U tilde. That's also a fast finite energy plane, asymptotic to gamma. Such that the images of U tilde and V tilde are different, then the images are disjoint. Then it follows that image U tilde intersected image V tilde is empty. And so the proof is so because V tilde is homotopic to U tilde, we have homotopy invariance. So homotopy invariance this implies that the Seefring intersection number of U tilde and V tilde is 0. And because of this assumption, we also have algebraic intersection number. So because image U tilde different from image V tilde, this implies that 0 is less than or equal to the algebraic intersection number U tilde with V tilde, which is less than or equal to the Seefring intersection number of U tilde with V tilde, which is 0. So therefore, we have the algebraic intersection number is 0, and then the result follows by positivity of intersection. We have image U tilde intersected image V tilde is empty. So this is, you always play with both intersection numbers. Both have, the advantage of the algebraic intersection number is that it has this positivity of intersection, and the advantage of Seefring's intersection number is that it's homotopy invariance. And then, so using this kind of scheme, you can prove many results. And as a corollary of this theorem, so under assumptions, of the theorem, assume in addition that, so we have, also U tilde is UA, and now assume that, so U is just the sigma part, so now assume that the U and V don't intersect, the images don't coincide. Assume in addition that the image of U is different from the image of V. This implies that the image of U is disjoint the image of V. And the proof is because image of U is different from image of V, we get that the image of U tilde is different from the image of the R shift of V tilde for all R in R. And therefore, by the theorem, we get that the image of U tilde is disjoint from the image of R star V tilde for all R in R, but because this is for all R shifts, actually the image of U has to be disjoint from the image of V. So it follows that the image of U, image of V, is disjoint. And so if to make a picture, we have, so we get now local. So as soon as we have a fast finite energy plane of Seefring intersection number 0, so we have local foliation. So they never intersect the asymptotic ring-orbit, and they're all embedded and disjoint from each other. So if assume we have U tilde fast finite energy plane of Sievering self-intersection number 0, then we have some local foliation. So we have here, always reduce the picture by one dimension. The orbit I draw like a point, so here is gamma, and then I have U, and then I have the whole moduli space. And now, question if you get global foliation, this is a question about compactness of this moduli space. And so let me mention the issues about compactness. So compactness. So this is, so let's suppose we have some finite energy plane. And so like this. So asymptotic. And then, so it can also look like this. So here I draw R. And you should imagine 2 more dimensions. But it doesn't look like this picture doesn't appear. Such a thing doesn't appear. This is not true. And the reason is we don't have local maxima, and that's because U tilde holomorphic. One can check using the holomorphic curve equation that so A is just mapped from C to R, and this map is a subharmonic. So the Laplacian of A is bigger or equal 0. So it's subharmonic, and therefore there is no local maxima. No local maxima. So there's a maximum. That's referred to as the maximum principle. But there is no minimum principle. There can be minimas, but no local maximas. And so you can imagine this R has 2 ends, plus infinity and minus infinity. But the issue with compactness is you can go to minus infinity. And then this scenario we have to vary possible scenario. So we have this finite energy plane. So now we have a family, and now the family like this, and then this. And then it goes deeper and deeper. Then goes the limit. So we have here, it goes to minus infinity. So this is referred, so that's the limit. And so we have negative punctures. And so what we get then in the limit, this is some special case of SFT compactness. So what we get in the limit is some negatively punctured finite energy plane. And so this is kind of, it's called SFT compactness because it says this is the worst thing that can happen. At least we get such a thing. And then to actually get compactness, we have to exclude negative punctures. To get compactness, have to exclude negative punctures. And yeah.
It seems to me that there is some local maximum between the two.
All right. No, it's not. You have more dimension. So it's. Sorry. Yeah. We have. Yeah. Right. Yeah. So this is. Unfortunately, I have not enough blackboard. So you should imagine this is not the local maximum. This is kind of saddle point. But we don't see the other directions. Yeah, that's the point. Where here it will be an actual maximum. So also other directions go down. Yeah, thank you. And so what we have to make sure that there are no negative punctures. And now there are many clever tricks but to exclude this. But I want to mention two of the ways how to exclude this. And these are somehow the ways which you can, at least to my opinion, exclude in practice most easily. And we can only partially exclude in the restricted three-body problem. But so I want to talk about Birkhoff conjecture for the restricted three-body problem, and we only have partially proved. But if you can exclude prove two of these properties, then we could get Birkhoff conjecture. So that I want to mention this. So one way to exclude this is by energy, namely if you know that the asymptotic orbit here. So let's assume this is gamma. Let's assume that gamma is the shortest period among all periodic orbits. Then you can, using some energy argument, you can show this cannot happen. Also, let me run. So the energy argument assume so this gamma is periodic Reeb orbit of smallest period among all periodic heat orbits, then there are no negative boundaries. And so this period, so if as I maybe recall, so the period was, so we have gamma dot of t. In my convention is more the velocity. It's tau r gamma t, tau bigger 0, and this was the period. And this period you can also interpret as the action because it's a reflow. So tau you can also get as the integral 0 to 1 gamma star lambda, because so why is that? So if, maybe let's so gamma star lambda, this is integral 0 1 lambda gamma t gamma dot of t dt, and gamma dot of t is just tau r gamma t, and this is, so we take tau out, so this integral 0 to 1 lambda of r gamma t dt, but by definition of the reflector field, lambda r is 1. So this is 1, so this is just tau. So for reflows, the period corresponds to the action. And this is somehow important to keep in mind, because there is in the restricted topology problem, there is some issue with this period, because usually we'll reparameterize the flow. And so the flow of the restricted three-body problem after reparameterization becomes a reflow. So if you look at the actual period you experience in physics, this will not necessarily be the smallest one. So what you have to care about is actually this action, which for reflows corresponds to the period. So we have also. So also for IE, for reflows, period is action. And just a remark, the orbit of smallest period, this is also called systole. So that's, maybe you've heard this word. It's just a word, but because there is kind of some activity in symplectic geometry to find the systole. So if you hear this word, so don't be too much afraid. What it means, it's the periodic orbit of smallest period. So I mark periodic orbit smallest, or the more the period of the period of the smallest, the period of the periodic orbit of smallest period, the period of the periodic orbit of smallest period is called systole. So this notion is more familiar in people who work in Riemannian geometry, because there it's called the shortest geodesic. But there is recently now quite some work to see what kind of theorems for Riemannian geometry also hold in symplectic geometry and what is really an actual Riemannian phenomenon. Okay, so that's one way to get compactness if this binding orbit, this asymptotic orbit, is the system. And the other one is dynamical convexity. So dynamical convexity. And this is this dynamical convexity is again some kind of automatic transversality result. So similar to, so we proved yesterday that for a finite energy planes, we necessarily have to have Conny-Sender index bigger or equal 2. Now, a similar argument shows you that if all Conny-Sender indices are bigger or equal 3, then there cannot occur negative punctures for a fast finite energy planes. So dynamical convexity means, so if we have, let's assume that we have maybe S3 and lambda contact form. Is called dynamical convex if the mu Conny-Sender index of gamma is bigger or equal 3 for all gamma periodic Ray orbits. And then, so a binding argument shows that in this case, no negative punctures for finite energy planes can occur. So people who are familiar with Fredholm theory can also see this as, again, as some result of automatic transversality, because the virtual dimension is negative, but then actually there no solutions exist, again, through binding. And then, so a binding argument. If 3 lambda dynamical convex, and then there are no fast, so negatively punctured fast finite energy planes. And in particular, we have compactness. Let me make some remarks concerning this dynamical convexity. So, if you are familiar with, if you are working contact topology, then probably you have heard about this notion of over-twisted and tight. And this actually means, so if you're over-twisted, you're never dynamically convex, because if you have this over-twisted disk, you can produce periodic orbit of Condensender index 2. So this means actually that the contact form is tight, and that means that you can imagine your S3 this come so Eliashberg proved there is a unique tight contact structure on S3, and then you can imagine that, or you can interpret S3 or obtain S3 as a star-shaped hypersurface in C2. Also you can actually always think more concretely here. It's not some weird contact form, but it's a rather concrete one. So this always occurs if you have a star-shaped hypersurface in S3. As a remark, so if sigma 3 lambda is dynamical convex, then it follows. So if you have not heard about these words, then these are just words. but at the end, you just imagine this as a star-shaped hypersurface in C2. But it follows that psi kernel of lambda is tight. This is already as hard. So this is only also involves holomorphic curves. This is not obvious. Holomorphic curves, and then by Eliashberg, there is a unique tight contact structure on S3. It's a unique tight contact structure on S3. And then we actually, as a S3 lambda, can be obtained as a star-shaped hypersurface. In C2. So we have, also on C2, we have the radial vector field. So let's write points Z1, Z2, and this is X1 plus IY1. This is X2 plus IY2, and then we have radial vector field 1/2 X1 X1 plus Y1 dy1 plus X2 dx2 plus Y2 dy2 is X, and sigma in C2 closed hypersurface is called star-shaped if and only if this radial vector field is transverse to sigma. So you can, it looks like this. So we have here as a radial vector field. That's star-shaped. And then we just restrict the standard, also
to that, so sigma is boundary of some star-shaped domain.
Right. Yeah, right. Yeah, this is another way. Also, i.e. sigma is boundary of a star-shaped domain. So in particular, it's diffeomorphic to S3, and then this S3 lambda, this is contactomorphic, so to sigma, and you restrict the standard x1 x1 minus y1 sorry, x1 d y1 y1 x1 plus 1 half x2 dy2 minus y2 dx2 to sigma as a standard Liouville form on C2 restricted to sigma. So you can imagine your tight contact manifold. Good. So at first it looks very hard to check this condition because first it's not so easy to find all periodic orbits, and then it's also not big fun to compute only Sender indices. So if you really want to follow the definition, you think you have now to find first all periodic orbits and then check all the Condé-Sender indices. It can sometimes be done if the flow is easy enough, but in general this is not the way you do it. But there is a criterion, and this to Hofer-Wysotsky-Sender, namely a special kind of star-shaped hypersurfaces are convex hypersurfaces. If they're convex. And if sigma is convex, then it's actually dynamically convex. So that's a useful criterion to check dynamic convexity. Since then you don't. Well, it's also not so easy because to check that something is convex, this is not an easy topic. But it's still better than first to figure out all periodic orbits and then check that and then compute the Condé-Sender indices in many cases. So criterion for dynamical convexity for Hofer-Wysotsky-Sender if sigma in C2 is convex, like this, then sigma is dynamical convex. Good. So, well, I will convert. So, first note that the notion of dynamical convexity, this is a symplectic notion because this, you just need to compute you need to compute Condé-Sender indices, and these are symplectically defined. The question about dynamical convexity, this is not actually a symplectic notion because it asks you to find some convex embedding. But so you always have such an embedding, but this is not unique. it might be that I give you a star-shaped one which is not convex, but then you can find a different embedding which is convex. So, so as a remark, so dynamical convexity is a symplectic notion. So, where convexity depends on embedding. And here is actually an open problem. An open problem is find an example of a dynamical star-shaped hypersurface which does not admit a convex embedding. What do you, then I mean that it bounds a convex domain. So a convex, so that if you have 2 points and then you have the line segment is completely contained in this domain. Usually. Right. Also convex i.e. bounds convex domain. Also open problem. Also I guess it's open. No, you never know. But, so find an example of dynamically convex dynamic convex star-shaped hypersurface sigma C2 which has no convex embedding. So, or proof that they are equivalent, that you can always find convex embedding as soon as you are dynamically convex. But I think the community tends more to believe that there should exist this kind of examples, and there is actually a candidate for such an example. So there is a candidate to Abondandolo, Bramham, Chemiewicz, Lamau. This candidate has, also, it's an example of a dynamic convex star-shaped hypersurface. This is a dynamical convex hypersurface. And it has the following property. Either it does not admit a convex embedding, or it is a counterexample to a conjecture by Viterbo. And with following property, either not, either admits no convex embedding, or this counterexample to Viterbo conjecture. So, but Viterbo conjecture, I don't want to discuss much, but this is also related to systolic questions. So because if you have convex embedding, you have good systolic inequalities. And so for the people who were in Daejeon, Simpa-Nim school in Daejeon, there I talked about this, and I think there is also videos, so you can learn more about this topic. Good. Okay, so that's so far what I wanted to say to compactness questions. Then now let's start with restricted three-body problem. So restricted three-body problem. So in this problem, you have two masses. And these are referred as the primaries. And you have one massless body. One massless. And so two masses, this is a two-body problem. So this we can solve. And because the third body is massless, he does not influence the other two. So this is really this is really a two-body problem. But the two masses they attract the massless body. It seems it seems a bit strange that because it has zero mass that they still can attract him. But you actually see that yeah, this was what Galileo observed. So the mass doesn't play a role. So if you have the Pisa, this tower, and then here was Galileo, and so he threw things, so little things and big things, but there might be some friction, air friction, but otherwise they just fall down the same way. So you can ignore the mass. So that's why even if it's massless, it can still be attracted by these two masses. So these are also possible interpretations. Possible interpretations. And so this is probably the classical interpretation is how this problem arose was, so the two masses are the Sun and the Earth, and the massless body is the Moon. So the primaries, this is Sun and Earth, and the massless body the Moon. And since the Moon is difficult. So yeah, so Kepler figured out that if you have two bodies, then you have just ellipses. But once he wrote, completely desperate to his teacher, to Maslin in Tübingen, that, so you will understand, so the Moon is much more difficult than all planets together, because the moon is yeah, is attracted by both, and the two forces are of similar size. So it's rather hard to think of the movement as the moon just as a perturbation of a Kepler movement. So this is the origin, but then you can also interpret now the primaries. If you take Earth and Moon, and you take the massless body as a satellite, and or you could think of this as a double star, two stars, and the massless body as a planet. This is more recently we know that these kind of things exist, planets in double star systems. And so the goal of this restricted three-body problem is to understand the dynamics of the massless body. As a goal is understand dynamics of massless body. So maybe let us keep to the first interpretation. So I will refer to as the masses. I will abbreviate by S and E and refer to them as Sun and Earth, and the massless body is the Moon. And I assume that the Sun and Earth move around the center of mass in circles. So this is they are actually ellipses with small eccentricity. But so we look at the circular case. E move around common center of mass. Circles. So I need one parameter. This is the mass of the Earth. So we have mu in 0, 1, and mu is the mass of E. And my total mass, as a 1 kilogram is now the sum of the mass of the Earth and the Sun. That's my mass unit. So 1 minus mu is the mass of the Sun. And then by Kepler's law, I can have also E of t is then given by 1 minus mu cosine t sine t, and S of t is minus mu cosine t sine t. So we have here origin is center of mass, and then here we have S Sun like this and Earth like this. And then what Hamiltonian for the moon. So Hamiltonian is, that's just kinetic plus potential energy. So we have h. So I have q. Q is a position and p is momentum. This is kinetic energy minus then I have potential is mass of the Earth, mu divided by distance to the Earth. It's 1 minus mu, the mass of the Sun divided by distance of the Sun. This is Newton potential. So this is kinetic energy. And this is potential energy. Now, this is actually not a Hamiltonian we like too much. And so what is not so nice about this Hamiltonian, it depends on time, because Earth and Sun are on time. It's actually quite tough because it's even a Hamiltonian with time-dependent domain. So this it's what we call is not autonomous. Depends on time. This is bad. Huh? This is not autonomous, i.e., time dependent. And but this Hamiltonian, this is actually the Hamiltonian in the inertial system, or also astronomers also a sidereal system. So with respect to the stars. So let's call it maybe I, going for M in inertial system. And now to remedy this situation, we go in rotating coordinate system. In rotating coordinate system, in rotating coordinate system, so the Sun and Earth are at rest. So the Earth is now at rest, 1 minus mu 0, and the Sun is at rest at minus mu 0. And but to change from the inertial system to the rotating coordinate system, we have to do some time-dependent coordinate change. And the rotation, the generator of the rotation, this is angular momentum. So the Hamiltonian flow of angular momentum gives us the rotation. Also, so we have some time-dependent change of coordinates. And so we have the Hamiltonian now in the rotating coordinate system, HQP. This is 1/2 p square, still the potential terms. But then, because we do this time-dependent change of coordinates, we have to add this is angular momentum. This generates the rotation. So now, the good thing is now this is time independent. So, so note H is autonomous. Independent of time. And this, why is this so important that it's independent of time? Then if you have a Hamiltonian which is independent of time, it's preserved. So we have preservation of energy. So we have preservation of energy. Energy of H. And so this observation, this goes somehow back to Jacobi. And for some historic reason, minus 2H is called the Jacobi integral. But this is then preserved. This is a preserved quantity along the flow. On the other hand, now in this rotating coordinate system, the Hamiltonian is now not just kinetic plus potential energy, but we have this additional term, and I rewrite the Hamiltonian a bit I complete the squares, then we can get a better understanding what is the physical meaning behind these terms. So complete the squares. So I write HQP as 1/2 P1 plus Q2 square plus P2 minus Q1 square minus mu distance to the Earth, mass of the Sun divided by distance to the Sun, and then because I completed the square, I have to subtract minus 1/2 Q square. And so what you see here, so now the last three terms, this is again just depends on Q, independent of P. So this called UQ. This is the so-called effective potential. But it has now one more term, not just, so we have gravitational force of the Earth, gravitational force of the Sun, plus this term, and this last term, this is responsible for the centrifugal force. So if you go to merry-go-round, so you will feel, some force out. So this last term, this gives rise to centrifugal force. That then we also have a twist in the kinetic energy. And this twist, this is responsible for the Coriolis force. So this is, if you just stay put on your merry-go-round, you don't will feel it. But if you start moving, then you will feel some velocity-dependent force.
Excuse me?
Yeah.
Do we assume the system is planar?
Yeah. All right. Right. Yes. That's right. We actually consider the planar case. We assume that the moon is in the same plane as the Earth. It moves in the ecliptic. Yeah. Right. So we planar. M is in ecliptic, i.e. plane spanned by E and Earth and Sun. Well, so far it would be not a big deal also to consider the spatial case. It's basically the same thing. You just have then one more coordinate here. So we have here twisted kinetic energy, and the twist, this gives rise to Coriolis force. This is some velocity dependent. This is quite different from these three forces. These three forces just depend on the position, but Coriolis force depends on velocity. You have a similar thing in the theory of magnetic fields, where you have the Lorentz force. Lorentz force also is velocity-dependent force, and this kind of Hamiltonian, where you have a potential and a kinetic part, twisted kinetic energy, this is also referred to as a magnetic Hamiltonian. So we can, in these rotating coordinates, we get a time-independent magnetic Hamiltonian. Good. Now, because it's autonomous, we can energy is preserved, so we can look at energy hypersurfaces. So H autonomous. So H is preserved along Hamiltonian flow. Along its Hamiltonian flow. And so if you have C in R, we abbreviate sigma C. This is H inverse of C. And this is the level set or energy hypersurface. And this is now a hypersurface in the cotangent bundle of, so Q is defined, the configuration space is the whole plane except E and S. They're the Hamiltonian singular. So we have to remove from R2 E and S, or this is just trivial bundle, so it's R2 E S times R2. So we have a hypersurface in this four-dimensional phase space. And now we would like to see how it looks like. And so to analyze sigma C, we look at its shadow. So this is four-dimensional. So a three-dimensional thing in four-dimensional thing is already, my blackboard has not, it's a bit, only 2 dimensions. So let's analyze something 2-dimensional. So we look at pi from T star R2 to R2 QP to Q. So just look at the position space and look at the Hills region. This is KC. This is the projection, the shadow of sigma c. And because of this form, you see as this first term, this is non-negative. So I can also write this Hills region as a sublevel set of the effective potential. This is also the Q in R2 except E and S, such that U of Q is less than or equal C. So this Hills region depends on C, and as you know from Morse theory, it will change when we cross a critical level. So what are the critical points of H? So we have the critical points of H. So we first note the following thing. So critical points of H are in one-to-one correspondence between critical points of U. Because this is just this is just quadratic. So we have a bijection crit H with critical points of effective potential. We forget just about P. And now this is a calculus exercise you can give to your students. There are 5. And these 5 are called the 5 Lagrange points. And they are, I will be now sometimes a bit sloppy and freely interpret them sometimes as critical points of U and sometimes as critical point of H. Now on U I can draw it better now than on the blackboard. So they are located like this. So we have, so here is the origin, the center of mass, and then here we have the sun, and here we have the Earth, and then we have the first 3 Lagrange points. They were actually already discovered by Euler. So this is L1. Then we have here L2, and then here we have L3. They are all collinear on the axis, E and S, and then we have L4 and L5. And L4 and L5, they are symmetric with respect to reflection, which is also clear because there is a symmetry in this restricted three-body problem, namely it's invariant on the reflection at the x-axis. And so we have, if you interpret them as critical points of U, then L1, L2, L3, they are saddle points of U. And if you interpret them as critical points of H, so you get here 2 additional positive eigenvalues. So they have Morse index 1 as critical points of U, respectively Morse index equals 1 as critical points of H. And L4 and L5, they are maxima for U, or have Morse index 2 as critical points of H, as Morse index. so what I should have said here is that this is true if mu is not 0 or 1. so that we don't consider the extremal cases where either the Earth or the Sun has mass 0. So here is for mu different from 0 or 1. And now their action is ordered in the following way. So if mu is between 0 and 1/2, so that means the Sun is heavier than the Earth, so i.e. S heavier than Earth. So we have HL1 is less than HL2 is less than HL3 is less than HL4 equals HL5. And H of L1, because this term at the critical point is just 0, you can also interpret this as U of L1 by all shifting between the interpretations, critical points of H and critical points of U. This is also U of L1, U of L2, U of L3. And if mu is between 1/2 and 1, so that means the Earth is heavier than the Sun, then you can just rewrite, just rename, call the Earth Sun and the Sun Earth, i.e. Earth heavier. Yes, so there we have then L2 and L3 change their role. Then we have just HL1 is less than HL3 less than H2 less than HL5 equals HL4 and L5. And if mu is 1/2, then everything is symmetric. So if mu equals 1/2, then we have here the Sun and the Earth, they are both symmetric around 0, and L1 is actually at the origin, and then L2 and L3. So now you can also just reflect, and yeah, L4 and L5 as well. So there we have HL1 is less than HL2. Now it's equals HL3, and this is less HL4 plus HL5. So now let's assume mu is 0.1/2. Then we have, how does the Hills region looks the following. So first, if C is less than first critical value, then we have 3 components. So we have one component around the Sun. We have one component around the Earth. and we have one unbounded component. So let's call this KCS, KCE, and KC unbounded. So that means the moon is either close to the sun, close to the, that's not very, in the example of the moon is maybe not fit so well, or it's close to the Earth, but what our moon actually is, or it's a comet. It could also be far away. And what, so he'll actually use this, so this somehow implies some kind of stability of the moon, because the moon is actually here in this region, so he cannot go close to the sun. He cannot cross this. So then also M either close to E or S, or a comet, i.e. far away. And then if C is between HL1 and HL2, then what happens is there opens a neck here. So here is L1. So we get now one connected component containing S and E, and still some unbounded component, K, S, E, this. Between is still forbidden. And then if you go further, if you go above the second Lagrange point, then you will open, here opens a neck, then all three regions are connected. Then if you go above HL3 here, another neck opens, and if you go above HL4, L5, then the Hills region becomes everything. Okay. So for the moon, I don't want to discuss the case of comets. So let's assume here. Close to the Earth. So it doesn't matter much of close to the Earth or close to the Sun, since you can always rename. So this is completely analogous. So let us assume that we are close to the Earth. So let's look sigma C E. These are the QPs such that Q is in the Hills region around the Earth. So the connected component of the energy hypersurface above these components for C less than H L1. And we would like to understand topology. But this is not yet so good for holomorphic curves. Because now Hills region is bounded, but this component of energy hypersurface is not compact. And this is due to collisions. This is, unfortunately, not compact, and this is because of collisions. But now the good thing is, so these are just two-body collisions, and at least for mathematicians can two-body collision, they can always regularize them. So if you, yeah, but probably if you are an astronaut, you don't like so much this regularized collision orbits. But for mathematicians, two-body collisions can be regularized. This is kind of old story, but let me, and there are different ways to regularize them. So let me, this problem already arises in the Kepler problem, and for didactical purposes, I would like now to explain the regularizations in the Kepler problem, and we can also do then this for the restricted three-body problem. And so I would like to discuss the regularization of the Kepler problem for negative energies, which was as explained by Moser. Regularization of Kepler problem for negative energies by Moser. So Hamiltonian for Kepler problem this is just H from T star. Actually, yeah. Let's maybe consider planar Kepler problem. So R2 origin to R. QP goes to 1/2 p square minus 1 over q. And let us, also for didactical purposes, I would like to consider the energy, energy minus 1/2, because there it's you see best what's going on. So we look at energy C equals minus 1/2. So maybe I add here 1/2 and then make the whole Hamiltonian 0. So let's look at sigma equals H inverse of 0. This, if you don't add this here, this means you have energy minus 1/2. Now, let's define a new Hamiltonian. So define K PQ. This equals Q times H QP. This equals 1/2 P square plus 1 Q minus 1. So, do you see? Do you recognize something? Now, before Q was position, P was momentum. But we are mathematicians, we are symplectic geometers. For us, it's not, distinction is not really important because we can also interchange their roles. As we have so note, we have from T star R2 to T star R2, if we have QP, P minus Q, this is symplectic map. The symplectic form here is just dq1 wedge dp1 plus dq2 wedge dp2, and if you to change like this is symplectic. Linear symplectic map, but if you think of it physically, it's a bit strange map because it interchanges the role of base and fiber. So interchanges fiber and base. So we have old position. This corresponds now to the new momenta, and the old momenta this corresponds to the new positions. So, but with this in mind, now we think, I've already here written P first and Q next. So now think of P as position and Q as momentum. Then this here is like length of Q, or co-length. The Q is maybe co-vector. And this is a metric. This is metric coefficient. And if you go back to your lectures on curves, surfaces, then this is the one, the cometric you obtain by stereographic projection from the sphere. So this is the cometric of the round S2 in stereographic projection. So this here is kind of length of Q with respect to cometric of round S2 via stereographic projection. And in particular, if it's just length, if your Hamiltonian is length, then the Hamiltonian flow is geodesic flow. So it's first geodesic flow in one chart. So you have this here your S2, then you do stereographic projection to so you have a chart except the North Pole. North Pole is missing. So the Hamiltonian flow of K, this corresponds to the geodesic flow in on S2 in chart by stereographic projection the North Pole. So how are how are these Hamiltonian flows of H and K related? So note, so if we, so this is a product. So differentiating products is somehow terrible because of Leibniz rule. But if we now just restrict to sigma, so if we look at K restricted to sigma PQ, so we can, and this sigma we can also think of K inverse of 0. Then this is, by Leibniz rule, we have first QDH restricted to sigma, QDH P, but then the second term is something H differential of Q, but H is 0, so the second term vanishes. So that means, and then Hamiltonian vector field, so recall, we have the Hamiltonian vector field is this is implicitly defined by equation dH equals omega. You plug in the vector field in the second component, and because of non-degeneracy of omega, this vector field is uniquely determined by this. So then, if you have this, so we get the same relation for the Hamiltonian vector field. So xk restricted to sigma pq equals qxh restricted to sigma qp. So that means they are just parallel to each other, and that means the flow of xk is just a reparameterization of the flow of xh. So that follows also the flow of xk is a reparameterization of flow of xh. So after reparameterization, the Kepler flow becomes the geodesic flow on S2 in one chart. This is not the whole flow on S2, because you're not allowed to go to the North Pole. So after regularization, after reparameterization, the Kepler flow corresponds to geodesic flow on S2 missing North Pole and North Pole. So we have here just geodesics as long as we don't go through n. But now we add, so regularization now corresponds at the North Pole. So regularization at actually also the fiber, because we are a cotangent bundle, add fiber over n. And then the regularized Kepler flow then corresponds to the geodesic flow on S2. So then the regularized Kepler flow geodesic flow on S2. And what are the geodesics to the North Pole? They correspond to collisions. So geodesics through n, they correspond to collisions. And so how can you interpret this physically? It's like you build in a trampoline. So you collide, then you bounce back like this. And then if you collide, so now we regularization, we interchange position and momentum. So the momentum explodes, so the velocity becomes infinite, and then we go over the North Pole, so we are on the other side. So the velocity is first very big in this direction, but then it becomes very big in the other direction. Then you bounce back like this. And another interesting thing to note, so the Kepler flow is almost periodic. So all orbits are periodic except the collisions. There you die. But then after this regularization, you get the completely periodic flow. Then because all geodesics are coming back. So maybe let's note, also Kepler flow, this is almost periodic. So the ellipses are periodic, and the collision orbits, they are not periodic. And then the geodesic flow on S2, all orbits are periodic. And so you just bounce back. So you collide, bounce back, and then you do it always like this. And this is also periodic. So we have here, so if we have here collision, then we bounce back. Go back and forth forever. So this is my bit strange, maybe, but so let me also, for mathematicians, give a bit different description, because which might be easier for mathematicians to understand what's going on. And this is because here we don't care about time. We reparameterize the flow. So there is a way to describe, if you just think of the flow as a foliation, if you forget that parameterization, we have just foliation, and then we don't need to care about time, and so we just extend the foliation somehow. And let me explain this a bit different language. Explanation of regularization in terms of Hamiltonian structures. So we have sigma. This is odd dimensional manifold, and now it's not we now don't have contact form, but we have a Hamiltonian structure which is kind of an odd dimensional symplectic form. So definition, a Hamiltonian structure omega in 2 form on sigma is omega on sigma is omega such that first the omega is 0, is closed, and we can't require it's non-degenerate, but what we require is that the kernel of omega is a one-dimensional distribution. So how do these Hamiltonian structures arise? This is if you have a symplectic manifold, you have a hypersurface in it, and you restrict your omega to the hypersurface. So how, let's go maybe sigma omega is called Hamiltonian manifold. So how do Hamiltonian manifolds arise? So you have M omega symplectic manifold, and you have sigma in M regular hypersurface. Then we have sigma omega restricted to sigma is a Hamiltonian manifold. And then because this kernel of omega is a one-dimensional distribution, so we get the foliation. So if sigma omega is a Hamiltonian manifold, then kernel omega gives one-dimensional foliation on sigma. So we have through each point we have a leaf given by the kernel of omega, and these leaves, they correspond to the trajectories. If you have here a Hamiltonian, and then the Hamiltonian vector field just spans this kernel of omega. So these leaves, they are the trajectories of your Hamiltonian vector field, but we don't care about parametrization. And then a regularization of a Hamiltonian manifold, if sigma is non-compact, this is just an embedding into a dense embedding into a compact manifold.
What mean regular? Regular hypersurface?
Also, or the hypersurface, also no singularities.
Yes.
So it's the hypersurface, non-singular. Yeah. Remark, if n omega is a symplectic manifold, H from M to R smooth, Hamiltonian, and here is regular. Zero is a regular value of H. 0 is a regular value of H. And then sigma is the level set. Then the kernel. So if x is a point in sigma, then the kernel of omega x, this is spanned by the Hamiltonian vector field at x. That's the one-dimensional subspace spanned by it, and then the leaves, they correspond to trajectories of xh, but parametrization this is omega x restricted to sigma. Parametrization forgotten. Now if sigma omega is a non-compact Hamiltonian manifold, then regularization of sigma omega is an embedding of this delta from sigma omega into sigma bar omega bar, where sigma bar omega bar is a closed Hamiltonian manifold. The sigma bar stands, and the pullback of omega bar is omega. Then you extend the foliation here to foliation here. And this we can now do also for restricted three-body problem. So we have also back to restricted three-body problem. So we assume C is less than the first critical value, and then we have sigma C E in T star R2. And then we embed sigma CE into the cotangent bundle of S2. Namely, what we do is we have first the map from T star R2 to T star R2, which interchanges fiber and base. And then we have here embedding into cotangent bundle of S2. You just think of R2 as chart of S2 via stereographic projection. And then, so then we have sigma CE bar. This is the, then we take the closure in T star S2. And the theorem we proved with Albers, Paternine, and Van Coort is that this here is fiber-wise star-shaped herein. where S2 is fiber-wise star-shaped. And this the fiber-wise star-shaped means if you restrict the Liouville 1 form, the cotangent bundle of S2, to this regularized hypersurface, you get the contact form. And so that that gives us then link between the dynamics of the restricted three-body problem and the what we discussed before. Now after, so we have to reparameterize the flow, as you see. So the flow is reparameterized, but after this reparameterization, it can be interpreted as a reflow here. That then allows us to use these other theories we discussed in the first. And I will explain more tomorrow about this. The topology is RP3. So yeah, right. What is the topology? So for the geodesic flow, how to determine geodesic flow in S2? How to determine the geodesics? You need a point and a unit direction. So it's the unit cotangent bundle, the unit tangent bundle of S2, which is RP3. So this is diffeomorphic to RP3, but then its universal cover is S3. Fiber-wise convex is a good question. I don't know in general. I know it. Chun-Yong Lee proved fiber-wise convexity for a limit case of the restricted three-body problem for Hill's lunar problem. There it's actually fiber-wise convex, and then you can interpret the flow of the restricted three-body problem as a Finsler flow. But I'm not sure if this is always true for all mass ratios. Finsler flow would be a more special reflow.
How is the contact form?
So you have here the Liouville 1 form, and you restrict the Liouville 1 form to this here.
It's tight?
Yes. This is because it's fillable. It's fillable, and then therefore tight. And yeah, there is also the universal cover is S3, and there is also an embedding, a direct embedding into S3, which is called the Levi-Civita embedding. So you can also, this is even older than even before Moser. You all had the Levi-Civita embedding, and then you can realize the embedding to the universal cover as this Levi-Civita embedding. Good. So then I think we continue tomorrow at 10.